Hello, everybody. Welcome to this session, LinkedList to ArayList, the full story. I hope you had a good coffee and a good night of sleep, and that you won't be sleeping the whole morning in this session. By the way, I'm not Venkat. If you plan to attend to Venkat's talk, it's the other room up here, but it's probably full at that time. So, all right. So this talk is about what is the starting point of this talk. In fact, it's a tweet. Published about a year ago by Dr. Deprecated. Who is this guy? Who tweeted, should Java util linked list be deprecated? Discuss. And then the discussion went on. Another guy showed up, Ken Fogel, who is a very serious man in the area. But by the way, Dr. Deprecated is also very serious because, in fact, Dr. Deprecated is Stuart Marks, who is working on the collection framework currently. And about 20 tweets later, he decided to write a blog post explaining the why of this discussion and the conclusion of it. This blog post is really very interesting. Of course, it's still online. And in fact, the conversation did not end here. I had a very good news this morning while having coffee to discover that even this morning there was one more tweet about it. So apparently, I just had to add this slide just to try to be complete in this presentation. Really, I had something else to do at that time, but I felt that it was quite important to do it. And Richard Warburton said yes, linked list should be deprecated, and it took him less than a minute to provide this answer. Okay, so that's the end of the talk, really. Linked list should be deprecated, and that's it. Thank you very much. Have a good morning. So we will take a little less than 3 hours to answer this question. And in fact, this could look like a troll, but it's not. It's a very interesting and very serious question that we are going to answer this morning. By the way, my name is José. You can follow me on Twitter. My hashtag is José Paumard. I'm a member of the Paris Java user group and have various content in various places on the internet. I'm a member of the JCP, the CDI expert group, and I give talks here in Devox in Java 1. I also have a free available course on the Microsoft Virtual Academy about Java. Yes, there is Java content, even on Microsoft Virtual Academy, and also online courses on Pluralsight. If you have questions during this talk, what about using this hashtag, listj9? I know that these rooms are really big and it's quite hard to raise your hand and shout a question so loud that everybody will be able to hear it, even me. So Twitter is a very reliable channel, and I'll try to take a look at the question during the break and answer them at the beginning of the second part of this talk. All right. So let's list J9 if you have questions. Okay. So the first conclusion we could write following this question is that this discussion, ArayList versus linked list, is clearly not a troll, even if it looks like one. And the real question, in fact, is there one implementation better than the other? And what is funny, or at least singular, is that the answer to this question was not the same 20 years ago when linked lists and ArayList were designed than now. Things have changed, and they might also change in the future, who knows? And the nice thing is that, yes, there is an answer to this question. There is an answer to this question. In fact, to fully understand this answer, we need to understand many other things, from algorithms to CPU structure, to patterns, to use cases, to many things. And once we have answered, as I almost fully this question, we will see that many other questions will arise, and many conclusions will be written that we can leverage to write better applications and to write patterns in a better way. So this This talk will be divided into two parts. The first part will talk about algorithms, complexity of algorithms, a little, implementation, quite a lot, CPU architecture and the notion of cache friendliness. We will see that in slide details, and also pointer chasing. There will be slides, there will be bullet points, so very good ways to have a good nap in the first part of the morning. And in the second part will be mostly live coding. We will try to provide implementations of list, set, and maps in very special ways to try to improve the performance of ArayList itself. Okay. So hardly any slides in the second part. Still some bullet points, because I know that we all love bullet points. Okay, so where to begin? In fact, there are several ways to begin, several starting points to begin to build an answer to this question. The first one being algorithms. The second one being implementation of functionalities versus CPU architectures. And the third one being use cases. So let us begin with algorithms. The first thing we can say is that it's really trivial. An ArayList is built on an array. Okay, I guess this is what is called ArayList. And LinkedList is built on a LinkedList, and I guess that the name comes from there too, right? And we have results on that. If we take a closer look at the basic operations on lists, the first set of operations is create and modify. We can add an element either at the end or at the end of a list, which is just an add method, or somewhere in the middle of the list, which is an add with an index. We can also remove an element by giving the index of this element or by giving this element itself. It will not be the same. And we also have a contains method that will check if a given element is in the list or not. And we also take a look at two methods introduced in Java 8, the removeIf method and the sort method from the list interface. Okay, so let us take a closer look at the basic operations on list, and let us have a look at how it works really. So the add method, there are two flavors of the add method. I can provide the object I want to add to the list, and this object will be added at the end of the list. And I can also provide an index, which is the place where I want this object to be inserted in the list. By the way, if I want to build lists of ints as primitive type, I might have an issue. Well, not with the add method, but with the remove method. Okay. The remove method works in almost the same way. I can provide the elements I want to remove, or I can provide the index of that element. If I take a look at this, I see that, in fact, if I add index object or remove index, the first operation I need to conduct is to find in my example, the 12th cells of this list. I need to get a pointer on the right cell of this list, which can be costly if it's a linked list, for instance. The sort and the removeIf are new methods introduced in Java 8 thanks to the default method mechanism that allows one to add method to existing interfaces without breaking the existing implementations. It works, the sort method just sorts a list in place, which is great. I do not have to use collections.sort factory method anymore if I don't want to. And the removeIf method takes a predicate as a parameter. This predicate will be applied to all the elements of the list, and the element that match the predicate will be removed from the list. We will check the source code of this method because I think they are very interesting to check. They show us how a very nice mechanism of default methods in Java 8 can be leveraged to add methods to existing implementation and still to have optimizations behind. Okay, so the read operation, we saw the modification operation of a list. Let us have a look at the read operation. The first read operation is, of course, the iteration over the elements of a list. I just take an iterator and call the next method to go from one element to another. I can also read an element from that index, from an index, and I can, in Java 8, build a stream on the list. So the read operations are the following. I can call this for each method, pass a consumer to it, and this consumer will be applied to all the elements of a list. Inside it, it will create, in fact, an iterator. I can also get an element by its index, get 12, for instance, and I can also create a stream on that list. This get by index is, in fact, can be seen as the first operation of the remove by index or add by index when I want to insert a given element in a given list. So, in fact, this operation is extremely important to understand since the performance of this operation will be reflected in the performance of other operations. Okay, so let us first have a look at the ArayList and let us see how it works from an algorithm point of view. It's built on an array, so we know that on an array, accessing the nth element of an array is something that is almost free. It's just arithmetic on pointers. We do not have arithmetics on pointers in Java, but we did that in C language or C++, and it works the same, in fact, under the hood. So adding an element should be almost free, since adding an element with an index should be almost free, since locating this element in memory is itself almost free. But ArayList has this kind of magic that I never deal with the size of this array. If I had an array, I would have to deal with the size of the array all the time, but ArayList hides this mechanism for me. So when I insert elements in the array of ArayList, there are things that are executed under the hood and that I do not see, in fact, when I just run some code. The insertion, in fact, will create a hole in the array to put the element at the right place. And creating the hole in the array implies to shift the elements of this array from one cell to the right. And the deletion will create a hole in the array, and this hole has to be filled, so it just shifts the elements to the left. Let us see that on this slide. If I want to insert an element at the nth place, okay, I need to locate this place in memory, which is almost free. But then there is a special piece of code that is going to be run here. This is a copy-paste of a portion of code from ArayList. What I need to do is take all the elements at the right of the insertion and shift them by one element to the right. So this is an overhead. I do not know at that point what is the cost of this overhead. Probably it's not completely free. And so, okay, and there is another thing in ArayList is that since I never have to deal with the size of the array. If the array is not big enough to hold all the elements I want to put in it, there is a special mechanism that will trigger that will enlarge the size of the array for me by a factor of 50%. So this is the same. I do not see this computation triggered, but it is an overhead that will probably have some cost when I bench things. Okay. By the way, growing a HashSet, maybe we'll check the code if we have the time. Growing a HashSet is much more expensive than growing an ArayList. So if you have the choice between an ArayList and a HashSet, well, you should choose an ArayList instead of a HashSet for that reason. It depends on other things too. Okay. So the insertion, I want to insert the element 1 at the nth cell. First, I need to locate this cell. And then I need to create this hole by just shifting the content of the array one cell to the right, all right, to properly insert the one element at the right place. This is great. And when I want to delete a given cell of the array, I need to locate this cell from the nth place, all right. I does create a hole in the array, and then I shift the element one cell to the left to fill the gap. Okay, so as a very early conclusion, accessing an element on ArayList is very fast. Adding at the end of the element should be fast if I do not need to grow the array. If I need to grow the array, then I have this system array copy that will trigger. And I'm not sure what is the price, what is the cost of this system array copy, so I need to check that. And random insertion and deletion, there is also an overhead due to the handle of the hole and the shifting of the portion of the array from the left to the left or to the right. By the way, there is something funny with ArayList is that if I keep adding and removing elements from it and check the code, I can see that this ArayList will grow and grow and grow as needed, but it will never shrink. So an ArayList, in fact, if you use an ArayList for a very long time in an application, it will keep the memory of the maximum elements it has held at a certain point of its life, I could say. So maybe it's a good idea to keep that in mind and to realize that sometimes you need maybe to copy this ArayList in another one just to be sure to free some unused memory. Okay, LinkedList. LinkedList is built on a doubly linked list. So the same goes, all we said for ArayList is the same for LinkedList, but this time accessing the nth element of an ArayList might be not as fast as an ArayList. Adding an element at the end of the list is almost free. Why? Because I have, in fact, inside LinkedList, I have a pointer to the head and to the tail of the list, the first element and last element. So if I want to add an element to the list, at the end of it, I just need to read the last pointer, add the element at the end, and that's it. And adding this element is just a matter of copying pointers, adjusting pointers in memory. So it should be fast. And there is no overhead as running a system array copy to enlarge the size of the ArayList, as it was the case for ArayList. But I can see that if I need to add an element at the middle of the list, since I do not have any pointer closer than the head or the tail, I have to go to the first element, then the second, then the third, etc., until I reach the right element of the list. And this is an overhead that should be considered. Looking for the nth element in an ArayList is obviously not something that is free, so I need to check that. Okay, so LinkedList is built on a double linked list. Access to the nth element needs to run through at least half of the elements of the list. So if I have many elements on this list, it might be costly. Adding at the end of it seems to be free, since it's just a readjustment of pointers. Insertion, once I have located the element where I need to make the insertion of element, inserting an element is almost free, since it's just a matter of moving pointers around. And the same goes for suppression. I do not have this overhead of system array copy. Here is the code, by the way, to access the nth element of a linked list. You see that I have the first test here. If just tell me if the element I need to check is in the first half of or the last half of the array list. This size greater than 1 greater 1 is in fact division by 2, written in an unreadable way. Okay, it happens. Sometimes in these pieces of code you have references to a book called Hacker's Delight. I don't know if some of you know this book. It's indeed a delight. You do? Yes, of course you do. Second edition. There was an updated edition recently. All right. This book is full of absolutely impossible to understand byte manipulation that will happen to compute n log of n+1 times the square of whatever. It's really very interesting, but kind of crazy sometimes. And it's used in the implementations of the JDK. There are references to this book in the comments. Right, so this is basically a division by 2, a fast one, fast way of divided an integer by 2. So if I am in the first part of the array list, I go from the first, which is the pointer, to the head of the list. Same for the last, it means that I'm going through the tail of the list, of course. And then I will have to take the first and the second and the third, incrementing this index pointer. Where is it? Yes, I++, until I reach the right place in the list to make the insertion or to get the element. So you see that this success is not free and will grow as the linked list grows. Okay, so access to the nth element, we have to visit all the elements of the linked list and count them until the nth is found. So we need to evaluate if this is costly or not compared to the system array copy I have to do in ArayList. But you see that the comparison of two is not that obvious. I mean, which one is the most costly? So far, I don't know. I need to measure that. This operation of visiting the first and the second and the third, etc., leads to an interesting stuff which is called the complexity of algorithm. In fact, getting the nth element of a linked list has a complexity of n. The notation is big O of n. We say big O because there is also another notation called small o, which has nothing to do with big O. So we have to make the difference between both. All right, O of n. What does this mean? This big O of n? It simply means that if I multiply the number of elements to process by 2, the time it takes to do the processing, to do the computation, will also be multiplied by 2 in the case of big O of n. All right. Generally speaking, the complexity of an algorithm is given by a function which is big O of something of n, a function of n, which can be n to the square, n log of n itself, log of n, etc., or 1. In fact, if I write a big O of a function of n, it means that this function is a polynomial of n, so alpha n2 plus beta n plus gamma. Okay, so this is big O of n2, in fact. And when n as part, if I write things like that, this is a simplification because I can have logs in the formula also, but generally speaking, it's correct. And when n reaches a given value, I can say that f of n it has almost the same value as n to the square times alpha, of course. All right, because the members in beta n plus gamma will become very small compared to n to the square of n. So this is what is important. But the problem is that this is pure algorithmic, this is pure computation, and this is valid for any value of n. The fact is, when I'm dealing with use cases, I'm not dealing with any value of n. I am dealing with the number of elements I have to process, which can be 100, 1,000, 1,000,000, 1,000,000,000, whatever. Okay. So in fact, this f of n should be evaluated, especially the coefficient alpha, beta, gamma, should be known with a good precision. In fact, because suppose I have a value of alpha which is 1,000, and I'm dealing only with 100 elements, it means that the dominant factor will be alpha instead of n. Okay. So I need to have a good idea of the values, of the numerical values of this formula if I really want to have a good idea of the performance of my algorithms and the way this algorithm will behave with the big values. Okay. Processing data is about math, of course, but it's not only about math, it's also about giving values to all these. And the fact is the theory might not apply very well to our use case. And this is what we are going to see in the case of LinkedList versus ArayList. If I want to compare the complexities between ArayList and LinkedList, if I want to compare the complexity of algorithms, all right, here I put 1, 10, 100, 1,000, and 1,000,000. The log of n, when we deal with the logarithm in computer science, it's always the log base 2. Okay, so the log of n of 1 is 0. The log of n of 10 is about 3 because 2 to the power of 3 is 8, so it's almost 10. 7 for 100, 10 for 1,000, and 20 for 1,000,000. So the logarithm does not increase very fast compared to n. Now, okay, this is the complexity of n. This is the number of operations I need to do if my algorithm has a complexity of big O or log of n. And this is n times log of n. This is the complexity of the quicksort algorithm, the well-known quicksort algorithm. So if I have 1,000 elements to sort, I will call my comparator about 10,000 times. This is a statistical result. And if I have a million elements to sort, I will call my comparator 20 million times. And this is the number of operations if my algorithm is n square. Now, you see that the complexity of an algorithm means the difference between an algorithm that I can apply to my data versus an algorithm that I cannot apply to my data. If I have 1,000,000 elements to process and an algorithm with a complexity of n to the square, it means that I have 1,000 billion operations to compute. And to have things in mind, what I need to know is that a processor roughly at the maximum will process 1 billion elements per second, with 1 billion operations per second. This is a good figure you can have in mind. So if I have 1,000,000 elements to process and the N2 algorithm, it will take at least 20 minutes to process. 1,000 seconds, that is 20 minutes about. If you want to go faster, if you want to go to the second, it means that you need to go parallel. But you need to make a factor of 1,000. It means that you need to have at least 1,000 CPUs to do the work. And just to reach a minute computing time. 1,000 CPU is not a machine that you can put on your desktop. It's probably in the cloud, probably a big machine. And if you want to go 1,000 steps further, that is, go from the minute, the minute to the millisecond, then you need to win another 1,000 time factor. So you need now 1,000,000 CPU to do the work. You need a big machine. Okay. So yes, it's too much. You can't do that. It's the idea. and of course this will be much more complex because this algorithm will not be able to run in a single JVM, most probably, due to many reasons. So you'll need to deal with parallelization among a lot of machines, among a cluster. Okay, so let's go back to the basic operation. So the add operation for ArayList and the set and the remove and the traversal using iteration is of complexity 1, basically. But you see that if you remember, 1 means that, in fact, it's not 1, it's alpha. There is a constant here. And when you need to add the index, to add at the end of the list or at the index, and that you have to grow your array list, there is some overhead here that is completely hidden behind this 1, and that we do not know for the moment. In LinkedList, the add at the end is of complexity 1 because I can reach this element just by traversing the tail pointer. But if I want to add an element at the nth place, then the complexity becomes n, even if it's n divided by 2, it's still n. Okay, but you see that the alpha in front of this n has nothing to do with the constant of the 1 of the array list, because the 1 of the array list is basically a system array copy, and the alpha in front of this n is the time it takes to go from one element to the other, which is not null. And it's the same for the set and the remove. The iterator, when we go from one element to another, once again, it's not the same 1. 1 is not equal to 1 in algorithm complexity. It might look weird because it's the case, because the one in the first case is the one that when you want to go from one cell of an array to another one, and in the linked list, it's the traversal of a pointer from one node of the list to the other one. So it's not the same. So we still must be cautious. We need to compare system array copy with a pointer traversal, which is obviously not the same cost. Is there a gamma? Remember, the gamma is the constant, constant overhead in the computation. Is there something that grows with n? Does the system array copy grows with n, for instance? This is hidden in the first evaluation we just did. And how? This is something that we need to measure, in fact, with benchmarks. And of course, are there any hidden costs that we didn't see? Most probably. But we need to check that, of course. All right. Let us go to benchmarks, because now that we have set up the problem, we have a fair knowledge of what is happening. We need to measure the performance of all these operations. Starting from a few years ago, we have a standard tool now in Java to do benchmarks, which is called JMH. JMH is a very nice tool, not that easy to use and to set up, but once it's done, it really gives you very reliable results. By the way, it is the standard tool to do benchmarking in JVM, and it will be distributed as a standard tool with the Java 9 distribution. What is a benchmark? Basically, it's a Java class with annotations on it. With this Java class, there is a special Maven goal that will create a special jar with a benchmark in it. You run this jar, and it will do the benchmark for you and provide the results nicely set up in an array. Great. A bench class looks like this one. So it's a public class bench, right, with some content. We'll see that. And with annotations on it. I will not go into details with this annotation. It just works if you use that. And this is what I used for the bench we are going to see now. You need some dependencies in your project, in your POM file. Those are the two dependencies you need. The version I used is the 1.15, which was the last a few days ago. Might be 1.16 now, but okay. And inside the class, you can set up parameters, which is extremely handy. And the JMH engine will launch benchmarks with all the combination of the parameters you give. So here I have two parameters, size, which is in fact the size of the list, and type, which is the type of the list, linked list and ArayList. So here I have 3 values for size and 2 for type. So the benchmark will be launched 6 times, linked list of size 10, 100, 1,000, and the same for ArayList. Very handy. Once you've done that, you need to create create a method annotated with setup. Here it's just a big switch with all the different types of lists I have. So the first here is a list. I can use this nice stream pattern to create a list. Int stream.range 0 to size will just create a stream of 0, 1, 2, 3, 4, etc. of ints until the size value is reached. It will be mapped into a stream of string of characters with just the integer set as a string and collected in a collection, which is here an ArayList. And since I still want my setup to be as fast as possible, I create the ArayList with the right size so that it will not have to be it will not have to grow from size to size when this list is created. Note that the setting up of the elements are of course not taken into account in the bench. They are done before that. And then you need to provide a method that is annotated with a benchmark annotation, and this is the method that will be run by JMH and measured. So here it's just an add at the end of the list. Now you remember that when when the list is too big, there is a system array copy that is triggered before adding an element to the. Sorry, when the list is too small, there is a system array copy that is triggered to grow the list before adding the elements. So in fact, I did two benchmarks: one with the list that will not grow when the add is done, and another one that will grow when the add method is called, just to see the difference between both. Okay, the simple add with index. The worst value for the index is, of course, the middle of the list. It should not change anything for ArayList, but for LinkedList, it will be the worst case that we need to check. So simple add will be done here for LinkedList, and will be done twice with ArayList, with a big ArayList, big enough to hold all the elements, and with an ArayList that is just the size that will trigger the growth of the list. So here are the results for the simple add. So this is the add at the end of the list. It is not the same results as the one published in your blog, Stuart, because it's on my machine and not on yours. Fair enough. You should not take these figures just as is, because if you run them on your machine, you will obviously not have the same results. And if you have this has been conducted on a desktop PC. I could have done that, by the way. I also did that on a laptop. The results were quite different, and I did that on a laptop. It was weird. On the battery, so not plugged on the network, and with a very low battery, like 20%. And in that case, the CPU enters a kind of power-saving mode, and the results are completely different. Okay, so this is on a desktop PC, fully powered. Nice. You see that we already have a tiny difference between LinkedList and ArayList. Apparently, traversing the pointer to the head is slightly more costly than accessing the last elements of the array. The big ArayList is the ArayList that is going to be enlarged due to the fact that it's full when I do the add. So you can see also that the system array copy that is triggered when you grow a list doesn't seem to be very costly, in fact. Barely seen on this example. Okay. Index read. This is a read operation in the middle of the list. So I expect the worst performance on LinkedList, and I need to see the performance on the ArayList. And index set. I do not expect to have a big difference between the index read and index set, because it's just a matter of having a different operation on the middle of the list. The read will just get the cell in the case of ArayList. The set, the index set in the case of ArayList, will trigger the system array copy, since it needs to create a hold in the middle of the list. So we should be able to see that too. Okay, this is the performance for the indexed read. And you can see that for the ArayList, it's fairly stable, 2.8 nanoseconds, which is really fast, in fact. And for the LinkedList, here we observe the N effect. That is, as the LinkedList grows, reaching the 5th element, then the 50th element, etc., until the 500,000th element is more and more costly. And indeed, it takes 3.4 milliseconds. That is a lot more than 2.8 nanoseconds. There's a huge difference between them to reach the middle of the list. And for the set, you see that writing an element is a little more costly than just reading it. Okay? So there is, if we go back one slide, you see that 2.8 versus 3.4. So I have a bit more than half a nanosecond here, but it is a consistent result. You could say that half a nanosecond is really a tiny difference on the CPU that is able to conduct one nanosecond per operation. In fact, it is consistent. That is, if you do this test again and again, this test is already a statistical result. Okay, it's just not one launch of the benchmark; it's a launch of a bunch of tests on the average of it. Well, it's not exactly the average. It's something a little more sophisticated than that. But this is really consistent results. So we have a little overhead when we do a set versus we do just a read. For the linked list, it's almost the same, since half a nanosecond will not be seen on 3.4 milliseconds, in fact, of course. Okay, so we can see that on the read on the set, accessing the middle of a linked list is extremely costly, and is completely killed by the performance of the ArayList. Iteration. Let us iterate over the whole list. The first pattern is an iterator. So here I do a little more than iteration. I will, in fact, accumulate the elements and compute a sum. All right. It's pretty useless because my list is just 0, 1, 2, 3, 4, 5, 6, and I know that the sum of the nth first integers is there is a formula to give that. So I do not really need to run this to have the result, but I'm not interested in the result in itself. I'm interested in the bench, of course. And I can also do that using a stream with a list with a map to long string.length and do the sum at the end of it. Okay, so I have two patterns that will read the whole list in two different ways, using an iterator and using a stream. The result for the iteration is in fact quite funny also. I can see that I do not expect to see much difference between them, because it is really reading the cells of an array one after the other versus reading the nodes of a linked list one after the other. So the only difference between those two performances are the pointer traversal. I do not have any pointer traversal on the ArayList. I have in the linked list. And what I can see is that I have a consistent factor of 2 between what I observe for the ArayList and for the linked list. Probably the only explanation I have between those two is the pointer traversal precisely. Pointer traversal seems to be quite costly compared to just going from one cell to another. We need to explain that. The result for the stream is almost the same, and in fact is consistent with what I saw on the iteration. Okay, so I have kind of mysteries there. I told you that we would be taking a look at the remove if and the sort operation. We will do that in the live coding session after the break. Okay, so let us draw a first conclusion, partial and intermediate conclusion. It looks like the overhead of the system array copy, in fact, is not that bad. If we check the add operation and set up a list so that we are sure that the system array copy is triggered, we see that the performance degradation is not that bad. If I have a good idea of the size of my list, I can create a list of the right size upfront to avoid it completely. That being said, there is still an unexpected performance difference that is absolutely not explained by the algorithm complexity, and that we need to explain. And if we want to explain that, we need to visit a little the way the CPUs are organized and the way they are built nowadays. In fact, the multi-core CPUs work in a special way that we are going to see now. And there is a big important thing to understand, which lies in the communication between the real core of the CPU, that is the unit that does the computation, and the main memory of the CPUs. Between the core of the CPU and the main memory, there are in fact 3 levels of cache. The first level of cache is really the first level are the registers themselves. The access is extremely fast. Then I have a first layer of cache, which is called the L1 cache. The access time is about 1 nanoseconds. It's a small cache. It can hold only 32 kilobytes of code on data. Now, not such an old time. In 32 kilobytes, you could have a full computer with the OS, with the video memory, with everything. But now it's only a tiny portion of the cache of the computer, right? Times have changed. I've got a second layer which is the L2 cache, access time is 3 nanoseconds, and the size is 256. Those are rough design because it varies, of course, from generation to generation and from CPU to CPU. On a given CPU, I have several cores. A normal CPU has 4 physical cores and hyperthreading solutions. I'm not going to deep dive into this kind of details. And I have a shared layer of cache, which is called the L3 cache, with an access time of 12 nanoseconds. So you can see that between the access time of the L1 cache and the L3 cache, I have roughly a 10 factor between both. If I have several CPUs, physical CPUs on my main board, motherboard, okay, they will be connected through what is called a QPI, Quick Path Interconnection, I think. And the access time between both is 40 nanoseconds, so again, a little slower. And the main memory is accessed in 65 nanoseconds on top of that. Right. It's funny to see that in 20 years, the access to the main memory hasn't changed much, in fact. 65 nanoseconds was already the performance of that about 20 years ago. So once we've seen this architecture, the organization of the CPU, the question becomes, how can I write an algorithm that will take this into account and be fast? And being fast means I need to pull all the data as fast as possible to the L1 cache so that the CPU is permanently fed with data to process without being stopped ever. Writing good algorithm is not good enough. Knowing the complexity is not good enough. There is also something that I need to work on, which is to create a structure that is adapted to this CPU organization. What makes processing fast is the capacity to bring the process data in the L1 cache as fast as possible. Now, how is this data transferred from the main memory to the L1 cache? This is also something I need to have in mind. Every time the core CPU needs the data, it will check the L1 cache if the data is there or not. If it's not there, it is called a cache miss, and this data will have to be fetched somewhere else. In the worst case, it will be the main memory. Okay, so we'll consider this worst case. Roughly speaking, a cache miss is known to represent a loss of about 500 instructions. So a cache miss will really halt your algorithm. The CPU will be doing something else until the data is there to be processed. So this is really something you want to avoid if you want to have fast computations. Now, the L1 cache is organized in lines, and the transfers between the main memory and the L1 cache is done line by line. All right? Each line is 8 longs of size, that is 64 bytes of memory. So the data is transferred 64 byte by 64 byte between the main memory and the L1 cache we have. And here lies the big difference between ArayList and LinkedList, is that the elements of the ArayList are in an array, which are stored in contiguous zones of the main memory. So when I want to transfer an array from the main memory to the L1 cache, I will transfer them group by group of data by group of data. Of course, it depends on the type of data I have in my array, but it will be quite fast to transfer from the main memory to the L1 cache. The problem with the linked list is that all the nodes element I deal with are randomly spread over the main memory. So in the worst case, I will have to transfer them one by one from the main memory to the cache. All right. So transferring an ArayList to the L1 cache can be much faster than transferring a linked list. And this is where lies the difference of performances I have. This is where traversing a pointer becomes much more costly than transferring data from an array. This stuff is called pointer chasing, and pointer chasing is really something that can kill the performances of an application. Let us take some examples. I have a tab of int, very simple example. All right, a tab of int is just a bunch of int stored in contiguous zones of the memory. If I take the exact same elements, but this time in a tab of integers, a tab of integers is in fact a tab of pointers pointing to integer objects spread anywhere in the memory. Accessing the second array will be much more costly than the first one. Why? Because I have to traverse all the pointers from the array to the piece of memory where the data is. We can take a second example with the point class, which is a basic pair class. Point class has with two integers in this case. If I create a list of such elements, in fact my list will be a list of pointer. Each pointer will point to a point object, and each point object will point to the x integer and to the y integer. So if I want to reach the elements, the value of those integers, I need to traverse 1, 2, 3 pointers to have the full pair. With such a structure, my algorithm, in fact, will spend most of this time chasing pointers, trying to reach the data before processing it. And of course, it can kill the performances of my application. Clearly, the linked list with all the pointer traversal all around the place is not a structure that is well adapted to this kind of CPU. It is not what we could call a cache-friendly structure. Cache-friendly structure, what is it? It is a structure of data that will allow the transfer of the data from the main memory to the cache as fast as possible. As long as you have pointers, as you need to traverse pointers to reach your data, you have a structure that is not cache-friendly. There are other cache-unfriendly structures in the JDK. Skip list, the concurrent skip list map, would be another one. Another example is the HashMap. What is a HashMap? If I check the implementation of it, it's in fact an array of map.entry objects. Okay, so map.entry object is a key value pair, but the key, even if the key is an integer, it is in fact wrapped in an integer object instead of an int primitive type. So this key is in fact a pointer to a value wrapped here, and the value is a pointer to the value here. If it's a string, it's a string. And this map entry object is itself pointed to by a bucket of the list, which is basically a particular cell of an array. So in fact, this is the structure of a hash map, an array of pointer that will point to a map entry, that will point to a key, that will point to a value. So if you want to traverse a hash map using an iterator, for instance, it will be much more costly than traversing an ArayList of elements. And since the HashSet is built on a hash map, the same goes for the HashSet too. Okay, we can do a benchmark, the cost of iterating through a HashSet versus the cost of iterating through an ArayList. This is the same kind of benchmark we had, and we can see that we have a factor of between 2 and 4 for these iterations. So if you don't have very good reasons to use HashSets, and if you want to iterate over your data using a HashSet, maybe it's a better idea to use an ArayList. In fact, a HashSet is extremely efficient if you have if you want to call the contains method, because the complexity of the contains method in an HashSet is 1, and the complexity of the contains method on ArayList is n. So if you have lots of contains to compute, use a HashSet. But if you don't, maybe it's a better idea to use an ArayList. If we take a closer look at our benchmark, remember that we created the linked list in that way, in fact. Okay, I showed you the pattern with the ArayList, but with the linked list it was the same. If I check this carefully, I can see that, in fact, I begin to create strings of character. There will be, since this benchmark does only that, okay, create this list. So all these strings will be created in contiguous zones of the memory, and the same will go for the nodes of this linked list. So in fact, my benchmark was probably better than expected, okay, because the nodes of this linked list were in fact stored in contiguous zones of the memory. If I modify this way of creating the linked list to this one, this time if you take a look, for each object, I create a dummy list of 100 nodes, and I just take the first node of it. So I kind of spread out all the node elements of the final linked list all over the place in the memory. They are not stored in contiguous zones of the memory anymore. All right? And I can check, okay, I can call this linked list sparse linked list. This is what I did in the benchmark, and bench this list against the previous one. And indeed, if I do that, I can see that I have a consistency factor between 2 and 3, 4 maybe, between the first linked list and the second one. So this is clearly the effect of the spreading of all the node elements all over the memory versus the first case where the elements were still put in contiguous zones of the memory. This is the indexed iterate, and this is the indexed read. And indeed, I can see that I have also this degradation of the performances that is consistent. And this is the same for the index set. Okay, what I would like to do, in fact, and this is I'm not going to talk more about that, but if I ask myself, are there any other way to create lists? What I would like to do, and it's not possible in Java to do that, is to have a list of int being a primitive type. All I can do is a list of integer, but a list of integer is a list of pointer, so I will have to traverse the pointers to reach the stuff. In fact, there are a lot of activity around this stuff in the Valhalla project. I provided here the link to this project. The motto of the project is codes like a class, works like an int. All right, and the idea is to have value types that is a better layout of the data in memory to be cache friendly and to have better performances. All right, there are also other implementations of linked lists, of lists and maps and stuff like that. I provided here 4 projects that gives other implementations of collection lists, set maps, etc. Some of them are cache friendly, especially for maps. Eclipse collection, which was known as Goldman Sachs collections a few months or a few years ago, HPPC, Koloboki, and Trove. And there is a very interesting blog post at this link that compares all the performances of the different implementations of this of those frameworks. Frameworks. Okay, so the question now is, since the problem comes from pointers and pointers come from objects, could we be able to create lists without objects? If I'm able to do that, then I will not have any pointer chasing, because if I don't have any object, I won't have any pointer. Okay, so the idea, in fact, is how can we build? Excuse me, there's French here. How can we build implementations of set, lists, and maps, and iterators and stuff without any pointer chasing? Pointer chasing comes from objects, so can we get rid of objects in those implementations? And if you have a little knowledge of Java 8, there is this new tool in our toolbox in Java 8 called lambda expressions. And lambda expression is precisely about writing code which are not held in objects. So this question turns out, could it be possible to create implementation of sets, lists, and maps using lambda expressions without any kind of objects? All right. So I think it's a nice time to have a little break. No? Yes? You don't want to break? Yes, you do? Okay. Let us have a little coffee time. So after the break, let's take 20-minute breaks. Is it okay? Yes, 20 minutes. We'll talk about this new stuff we have in Java 9, factory methods for collections in Java 9, and the live coding session. Well, we show you how to create implementations of those using lambdas and without any pointer chasing. Thank you for your attention. I will be monitoring the Twitter hashtag I gave you at the beginning of the talk, and begin by answering some questions at the beginning of the next part. Thank you. Hello. So I hope you had a nice coffee. I see that there are still people in the room, so that's very good news. While you were having coffee, we were browsing through the questions, and I'm very glad to welcome Stuart Marks, also known as Dr. Deprecated, on stage, that will answer the question for me. First, sorry.
Thank you, José. So I'm not going to answer all the questions, but there are a few from Oleg Shelejev, who tweeted some questions to us that are on topic of linked list and ArayList. Actually, I should introduce myself. My name is Stuart Marks. I work at Oracle on the JDK group. I work on the core libraries team, and well, José went through the history of this, and so, the Twitter discussion that occurred last year, and boy, he decided to base an entire tutorial around it. So thank you for mentioning me, and thank you for having me up on stage here. And so this is, you think linked list versus ArayList. This turns out to be a very interesting topic, and in fact, while José has been speaking, I'm thinking, oh, there's another article I can write. Oh, there's another tweet I can. So there's actually quite a lot of stuff that goes on. Plus, there also, I think I have some API enhancements up my sleeve that we might be able to do. But anyway, so a couple questions here. So one, I think I'm not going to answer them point by point, but Oleg had a number of questions. One was, what's the best implementation of linked list for various definitions of best, performance, features, queues? Another question is, what is a good use case for a Java util linked list? And the third one is, should we deprecate linked lists and make everyone use ArayList or rewrite it? And so there's a lot of interesting issues packed into that. And so I think I'll just talk about that for a while. So one thing is, actually, maybe I'll retweet some of the original Twitter discussion, but Ken Fogel, who's the professor at University in Canada, so we had a long exchange, and that resulted in the blog article that José posted. One point of confusion we had was talking about java.util linked list versus linked structures in general. And there are many good reasons for continuing to use linked structures, even though they do have this difficulty with memory locality. In particular, I can think of a couple reasons. One is if you have an immutable persistent data structure, then it's very hard to express that in any way other than using a linked structure. So there's some research topics about that, and that's way beyond the scope, I think, of this tutorial. But that's a good reason to use a linked structure in general, as opposed to Java util linked list, which is a specific implementation of the list interface using mutable node objects that are linked together. Another reason to use a linked structure is in the JDK there is Java util concurrent, and there are a variety of concurrent data structures, such as, I'm thinking linked blocking queue is an interesting one. And so that's basically a linked list. It's a queue in a linked list format. But the reason for its existence is that it's a highly concurrent data structure, and so additions and removals, so additions occur at the end and removals occur at the beginning, and those algorithms are optimized for low contention non-blocking access. And so even though it has a linked structure, generally you don't traverse a queue. You have multiple threads pulling off the front, and so that's designed for a different use case. So even though it's the same organization as a linked list, the usage is very much different, and it's designed for highly concurrent, non-blocking access. So let's see, what other things were there? What's a good use case for linked lists? And so the obvious answer is none, but that's not true. And so even though I did propose deprecating linked list to begin with, there are some things that linked list does better than ArayList. But they're actually hard to find out. And so this is another article I need to write, which is what the use case is. So what José showed was that traversing a linked list is very expensive, because you have to hop from one node to another, and you are you are basically taking cache misses quite often, and that slows things down. So traversing a linked list, if you insert in the middle, that's very expensive because you traverse to the middle, do your operation, insertion or deletion or whatever, and then return. Now, what if you had many edits to do within one traversal? So suppose you had a problem where you had a list of elements and you wanted to say, for every element that matches a predicate, insert this extra element right next to it. So you're doing many edits on the same linked list and only traversing it once. And so if you think about things that way, ArayList has to do a lot of extra data copying every time you do an insertion. It has to shove the elements down the end. But linked list, it just, since you're right there, it just inserts a node at that position, and then you can continue the traversal. So what you do there is you amortize many operations, amortize the cost of traversal over many operations, and that actually is a use case that is pretty where linked list outperforms ArayList. Now the question is, how often do people do that? I don't know.
If it's your use case, I mean.
That's right. If it's your use case, then you need to do it. So maybe, and in fact, I have an idea for an API that can be applied to things like I think ArayDeck probably that can improve its performance over linked list. After which there will not be any use for linked list at all. The question is whether it's actually worth adding that API. And then the final thing is, should we actually deprecate and remove linked list, or should we re-implement it, and so forth? And that is an interesting question. I do not think it's worth actually removing it from the JDK. Maybe deprecating it to tell people that it is more often misused than used effectively, but not actually to remove it. It's probably not worth telling people to migrate their code. So could linked list be re-implemented to perform better in many of these cases? Possibly. It's not clear to me whether that would be a re-implementation of linked list or whether that would be just another list implementation. There are a bunch of ways you can implement lists more efficiently. Like instead of a single array, you could have a linked list of arrays. If you look in the JDK, there's something internal inside the streams package. It's not a public API, but it's a list-like structure called a spined buffer, which is an array of arrays. And so the streams package uses that for fast append-only access. And you could think about enhancing that so it is a full-fledged list interface and making that public. But I hesitate to call that a replacement for linked list. I think it would be you wouldn't re-implement linked list in that fashion. You would have it would just be a different list implementation. Or you can imagine a tree-structured list. Maybe have a tree list or something like that. So those are a few questions and some interesting discussion around that. Did you want to, any other questions that
there was apparently, because there is something weird happening currently in the US, and apparently there's somebody...
Devox Trump.
Devox Trump. Don't believe Devox media. Continue to use LinkedList, Vector, and Hash Table. They're great. Make Devox and Java great again. And you liked it, by the way.
Yes, yeah, it's very funny.
Okay, that's fine. Oh, I should switch this on.
Okay.
Okay.
Anything else? Or
I think we're
okay. I'll turn the floor back over to you.
Okay.
Anyway, thank you.
Thank you very much. Thank you, Stuart. All right. So where were we? Live coding. Great. Yes, I just wanted to mention a few things that are coming in the collection framework in Java 9, thanks to your work, by the way, Stuart. And Java 9 brings a question, is how to create, the question I need to answer now is how to create lists with objects in it, but without using a pointer. And that there is some new stuff coming up in Java 9. Suppose we want to create a list or a set or a map or whatever with elements in it, already elements, and maybe immutable. maybe without any nulls in it. In Java 8, and until Java 8, we have this weird syntax to do that. Maybe you never came across this wonderful syntax. Maybe you did. In fact, what does it do? It's really weird, isn't it? It looks like JavaScript. Okay. What does it do? In fact, it creates... This is a non-static initialization block. Okay, you have static initialization blocks. If you want to be sure that nobody will be ever able to test your code, you should really use that everywhere. But you can also, you have another tool which is much more sneaky, which is this one, non-static block of initialization. And basically it creates an anonymous class that extends HashMap, and it will execute those puts operations as part of the initialization of this particular HashMap, and then put those key value pairs in it. It is not immutable. If you want to be immutable with that, you need to wrap that in a collections.unmodifiable map. So it's a two-steps process in which somebody can interrupt you and get the stuff. So basically, it's hard to do. In Java, until Java 8, it's hard to create a list or a map with already stuff in it. In Java 9, we have a new set of patterns, which is really great. List.off, this is a static method of the list interface, okay, factory method. List of 1, 2, 3, and it will return me an implementation of a list with the right elements in it, of course, hopefully. Those implementations are immutables, which is great. I cannot put null values in them. If I do that, I will have a null pointer exception. And if I put doubles in a set, I will have a nillogal argument exception because I'm not allowed to put doubles in the set. And they're also serializable. The fact is that they do not allow null values is really great. Most of the time when I have a null value in a list or set, or if I have a null key in a map, it's a bug. And when I realize that I have a null key in a map, it's too late. I need to check out who put this key there, and it's a very hard work to do. All right, so this is great to have that. They also have a random iteration. That is, if you iterate over those implementation twice, in the case of a collection, of course, or a set, you will not encounter the elements in the same order. I will not go into details of that, but this is normal to have that. And there are optimized implementations. You don't really need to create an array if you have only one element in your list, do you? Okay. Maybe you do not need to create a full hash map if you have just one key value pair in your map. So there is room for optimization here. So we have a bunch of off factory methods on list, for instance, up to 10 if my memory is good, and vararg after that. Great. The case of the map is a little more complicated because you cannot, of course, create varargs with first the key, then the values. So you have a bunch of off methods with key value, key value, key value, key value, all right? And if you want to have more than 10 key value pairs in your map, you have also an off method on the map entry interface and create off entries with those entries as a vararg. And the off entry will throw an exception in the case of a double skid. Well, those methods will throw an exception. And you give a very nice example, the Stuart, of that. I would love myself to copy-paste it here, if you don't mind, which is this one. Okay? If I run this code, all right, in fact, there is a bug in this code, which is here. I put it here in red. This key appears twice in this list. When I just browse quickly through the code, it's not very obvious to see that. But if I run this code, and if this code runs well without an exception, I will have an exception or a bug somewhere else in my code, far, far, far away from this one. I will just discover that the column, the value associated with the column key is not the right one. If the last put wins, it will be pi, my in, whatever value linked to that key. and I will have lost the colon keyword. So I will need to check why is this wrong, and then go back to here to discover that in fact in the first place this map was not set up in the right way. So having having an exception at the beginning of this map is really the right way to go. I know that it's not normal to have a doubles in the keys, so I need to fade fast and throw the exceptions, throw the exception at once. All right, so this is just a glimpse at what we'll have in the Java 9, which is great. We're going to love those patterns, I'm pretty sure of it. The question I would like to ask is, how can we build optimized implementations of lists or sets or maps, whatever, without any pointer chasing, but only for small lists or maps with one or two elements? There are use cases for that, and if I know in advance the number of elements I want to put in the list, maybe I can leverage these kind of things. Okay, enough slides. Live coding time. Great, I love this. So I will take my clip. By the way, this is your blog, Stuart. I just have it here. All right. Oh, I told you that I was about to show you the implementation of the remove if and the sort method. It's really nice to see that. Yeah, so in the list interface, I need to get the right one. As a matter of fact, it's in collection. I have this remove if method in the list interface. Is it big enough? Does anyone want me to make the font bigger? No? It's okay? Right, great. So if I check this remove if method, what does it do basically? It calls, it goes through all the elements of the collection, all right? And we'll call the remove method on the iterator that is created from this list, from this collection. So if I go to ArayList, which is definitely the implementation I should be using, and visit the iterator, it's a private member class of the ArayList, and the remove method of this iterator is the following. Basically, what does it do? It just call for the remove method of the ArayList implementation. So if I check this remove method, I have the well-known code here. That is, I am going to remove this element from my list, and then using a system array copy, fill the gap that I just created by shifting all the elements of the list or one cell to the left. Now, if I have thousands of elements in my array list, and that, for instance, half of them are to be removed, it means that I will have to run this system array copy 1,000 times to fill all the gaps, which might be not that efficient in that case. I could probably do much better with that. Now, the fact is, those default methods in interfaces are used in case there is no concrete implementation in the implementing class. And this is resolved at runtime. So I can check if this remove if method is overridden in the concrete implementations. Indeed it is. And I have an implementation in ArayList here. So the remove if that is run when I use ArayList is not the remove if from the default implementation. It is the case for LinkedList, since in LinkedList, let us go here. You see that the only implementation known by LinkedList is the one from the interface. Okay, so let us check what does this remove if method in ArayList does. In fact, there are two parts in it. It creates a bit set. A bit set is a very useful a class from the collection framework that is just a set of bits, in fact. In the first pass, it will just go through all the elements of the list. This is this piece of code here. And will set all the bits of this bit set to 1 or 0, is it? I don't know. Never mind. Every time it come across an element that should be removed. This is the mark step. And then if there are any elements to remove here, it will go through this code, which basically goes from one element to be removed to the other and just readjust the index of the elements. So you see that the implementation of the remove if on ArayList is much more efficient than the default one implemented in the interface. The default method mechanism, in fact, allows to bring new functionalities to existing interfaces without having to re-implement them in interfaces, but it does not prevent you from using optimized implementations in your code. So if you have a better implementation than the one provided in the default method, you can use it and you can still be compatible with the API, which is great. By the way, this algorithm is a classical mark and sweep, which has been used in garbage collectors for many years. The second implementation I wanted to show you is the collection.sort. And this is the sort method. I'm going to take this one from Java 7, so before Java 8. This sort method just do a sort, all right? On a list, of course, because on collection the notion of order is not there, so it would be useless to use to sort a list, to sort a collection. That is picture time. Hello. So right. So how does it work in Java 7? It takes my my list, whatever this list is. It copies the content of this list in an array. This is what is done here, list.toArray. Then it sorts this array, and then it copies back this array to the original list. Maybe it's not that efficient to do things like that, because if I have, hello. Oh yes, more please. Thank you. All right, so maybe it's not that efficient to do that, because if I have an array list, the fact is I already have an array in an array list. But this code has to work for all the implementations of all the lists you can imagine. So even for ArayList, the array will be copied into another array, sorted, then copied back to the original array. This, what is our code doing until Java 7 since the Java framework, since collections.sort has been introduced in the JDK, which might be not that great. Now, in Java 8, in the list interface, which is, by the way, already here, I have a sort method, which is great. I can do now ArayList.sort, pass a comparator as a parameter, and have my ArayList automatically sorted for me. Now, the fact is that the code is almost the same as the one from the collections.sort. All right? So for ArayList, it is not optimized at all. But the difference now is that since it is a default method, it can be overridden in the ArayList class itself. And this is what has been done. So if I check the ArayList class, the sort method this time does not copy the array in a new array to sort it and to copy it back, which is, of course, a waste of both time and memory. It directly sorts the array in place inside the ArayList. So if you call ArayList.sort, it will sort it in the proper way, how you want it to be done, in fact, which is great. So now, okay, you say, all right, now what I need to do is to check all the collections.sort of my code and then replace them with a list.sort just to use this nice feature. Now, the fact is that you don't have to do that, because this is free beer. Great. If I check the collections class from Java 8 and not from Java 7, and the sort method, what I see is that the collection.sort method is now wired to the list.sort method, which is great, because I have nothing to do. Just moving from Java 7 to Java 8 will see my ArayList sorted in an optimal way for free. as in free beer. No, it's not great? Yes, I think it's great. All right. What about leveraging this kind of thing, default method, to do some implementation of lists? What I would like to do is create an implementation of a set. We're going to begin with this one. And the pattern I want to write is the following. I want, for instance, a set of strings. All right. And create it like that. Singleton set of 1. Okay. And this singleton set is for the moment, it's a class, right? So I'm going to create this static method inside. I'm going to ask Eclipse to do that for me. I want to put it at the beginning of the class. I created this abstract method just for things to compile, right? And this should return, well, something. For the moment, it just returns null. This should return the proper implementation of stuff. Now, this singleton set abstract class, for instance, is an implementation of set that should be immutable, that should hold only one element, and that should be optimal, hopefully. So, since it is immutable, I've got a bunch of methods that are not supported, all right? So the remove, remove all, retain all, add all, and clear method just throw unsupported operation exceptions because it is an immutable implementation. Now I still need, I've already written the implementation of toArray, and especially of toArray that takes a type as a parameter, because it's kind of a ugly implementation to get it right, so I'll just get rid of that quickly. Now, what I'm left is 1, 2, 3, 4, 5 methods to implement. The size, obviously the size, since it is a singleton set, the size is 1. Is empty, which returns false, because I have one element in this set. Contains object will return true if this object is equals to the object I have in my set. This object, I will read it with the get method, and we'll see how to implement that. Oops. So get equals O, right? The contains all of collection is a bit more tricky to write. Why? Because I might have several elements in that collection, and I could have several elements that are the same. So I need to check really all the elements of a collection to check if they are all inside this set or not. So this is a good way of, of using a stream pattern. So I can open a stream on this collection. This will stream all the elements of that collection. And for all the elements, check if that element is the same as the elements I have in my set. So it is the work for the allMatch method. So this is the element of my collection, and I want to check if get is equals to E. Okay, sorry, it's get. It's this get. And by the way, this is a nice method reference. I can ask Eclipse to write it for me. So it turns out to be gets column equals, which is nice. I could protect myself against those psychopaths around here that would send me a null collection, because I don't want to deal with null collection. Oh, by the way, if the collection is null, I could return false, in fact. Okay, no, I prefer to throw a null pointer exception. I shouldn't be called with a null object. It doesn't make sense. All right. So when I'm left with the iterator here. We'll deal with the iterator a little later. Now, we can see that all the implementation of this set relies, in fact, on the implementation of the get method, which is here. There are several ways to see this and to solve that problem in the same way, in fact. First, I can here recognize that this is a well-known pattern. This is, in fact, the template method pattern from the GOF. I have only one method to implement. And if I want to do that, I can implement it using an ugly instance of anonymous class. Sorry, I forgot how to write that. Yes, it should be like that. Add an implemented method, and this is the string I want to put in my set. So I can write it like that. It doesn't compile because I need to provide the string type here. I think so. No. Why doesn't it work? Oh, sorry. Thank you. Yes, that's right. Okay. So I can write it like that, and it will work. Okay. I provide an instance of an anonymous class. But then if I see that, I can see that, in fact, the only method I need to implement is the get method. I have an instance of an anonymous class that only overrides one method. And that should ring a bell. Maybe it could be a lambda. Now, lambda is something very, very specific. I cannot implement an abstract class with a lambda. A lambda should be an implementation of an interface. All right? But the question is, could this singleton set be an interface? In fact, I've got a bunch of methods here that are all public, but that probably could be default method instead of public method. So let us try that. Let us just make this abstract class an interface. It does not implement set anymore. It merely extends a set. Okay. This doesn't work anymore. It's quite normal. And all those methods do not compile. Why? Because I need to replace all the public keyword with the default keyword. Let us replace all. Okay. Yes, I need to put the public back here. I think I can get rid of this. Also this. And I think it's well done. Oh yes, this is not a default method. And it does compile now, right? Is it a public, is it a functional interface? I can just ask the compiler to help me here. And the compiler seems to be happy here. So this is indeed a functional interface. But since it is a functional interface, probably what I can do here, in fact, instead of returning here this instance of anonymous class, is just returning the implementation of this get method here, which turns out to be just this. Okay. Maybe I should return a singleton set here for this to work. All right. Maybe I can go a little further in the generics. We all love generics, don't we? And make this E and this E and elements. All right. Could I go one step further? In fact, this is it's a lambda, all right? That doesn't take any parameter, and that returns an element. And in fact, this lambda already exists in the functional interfaces package. It's a supplier. The supplier doesn't take any elements and returns something. So I could go even one step further, saying that this singleton set extends set and supplier of E, and get rid of this because it's already in the supplier interface. And you see that this is an implementation of set. There are two things I still need to do. First, implement the iterator method, and second, set up a warning, something. I need to warn you of something, right? Okay, but with this kind of trick, I am able to implement this set with a lambda, with a supplier, in fact. Okay, the iterator. I could create an implementation of iterator. I already created a class here. suppose this class implements iterator, no, not iterable, iterator of v. Okay, it's a singleton iterator of v. All right. And I need to implement two methods here, as next and next. In fact, there are three methods in iterator, but thanks to the default method, the remove method of the iterator class in Java 8 has been made a default method that already throw the right exception for me. So now when I need to implement an iterator in Java 8, I do not need to, well, if I do not want to support the remove method, I can directly, I can keep the default implementation if I wish. By the way, I also have for each remaining method in it. Okay. I can implement it using an abstract class. Suppose I want to return here. I could do it right now. Return a singleton iterator. This one. I don't want that. Of get, because this is the only elements I have in my set. Create the static method here. Okay, let us do it like that. It's a static method, so I need to declare the type of the iterator here, right? And I can see that I could easily create an implementation of it with a next and a as next method in a class in a classical way. What I would like to do is, in fact, to make this iterator also a lambda. It's a little more tricky than the set, because the set was only relying on one abstract method, the get method, and it was quite easy to see that it's a template method, and since I have only one method to implement, and an immutable class, a lambda does fit quite well in this pattern. Here I have two methods to implement, two different methods, and I have an internal state that is a mutable state. If I call next twice, the first time it should return the correct element, and the second time it should throw an no such element exception. So it means that inside this iterator, I have a state that is mutated by the calling of the next method. But the fact is that this state has only two values. So maybe I can do something here. Basically, what I want to do is sometimes return E, and sometimes throw a new no such element exception. Okay, so it doesn't compile, it's just to fix the ideas. So I want to create an object that can both return an element or throw an exception. So that can have two outputs. In Java, I cannot really do that. An object has, a method has one output. But I can use a trick to do that. I love tricks. In fact, I could say that I could create an object that is a supplier and have two instances of this supplier. First instance, supplier of E. Let's call it S1. I need to import this. And this will return, okay, I'm going to put it here so that I can access the E element. Okay, this is the supplier that will return the E element. And I can have a second supplier, same type. I'm going to call it S2. Okay, but this one, that will throw a new no such element exception. Okay, and those two objects have the same type. So I can use this object as an well, supplier of E as an internal state of my lambda and put in a place that my lambda can mutate. Now, I need to go a little further because an interface cannot have fields, of course, and the lambda cannot mutate the object it has access to. So if I want to do that, I need, in fact, to create an array. All right? The array in itself will be immutable. It will have only one element. And after reading that, I will mutate this only one element to the new object. Let us wrap this in a static method. Static supplier of V. For instance, for the moment, I'm going to call this method like that. Return this. OK. And I'm going to call this method no such element exception. I don't need this S1 anymore. All right. And when I do the next, I will need to read the first element of this array into a supplier. So do something like get of 0. And this should return a supplier of E. OK. I am going to return supplier.get. But before that, I need to mutate the internal state of this array to the new supplier that throws the exception. So do something like get of 0 equal no such element exception, which is this guy. OK? And of course, in this array should be initialized with the supplier that is going to return the E, which is there. All right? So if I call this code twice, this next method twice, the first time it will indeed return the right element, and the second time it will throw the no such element exception. This is when you have this pattern, I want first to return an element, then throw an exception. I can use this pattern out of the box to do that. It's not throw here, it's return. Excuse me. OK, so I need to provide an implementation for this get method. Since I am in a class, it will be, of course, abstract. And this get method returns an array of supplier of E. OK, does it work? Doesn't seem to be very happy. Ah, yes, this class should be abstract, of course. OK. And now it works. Great. And now I need to provide an implementation of this abstract class in the off static method, in the off factory method of this iterator. But then, in fact, what I did here is that I transformed this iterator in the same kind of pattern as the previous one. That now I have an iterator that relies on a get method, which is this one, and I need to provide an implementation of this only abstract method. All right. So I have the exact same pattern as the set I could solve in the previous case. So in the previous case, I solved this pattern using an interface and a lambda. So now I should be able to solve it in the same way using an interface and implementing it with a lambda. So this public static is not needed anymore. This is a default. And this is also, a default. Why doesn't it compile? Because here it does not implement, it extends iterator. And it compiles. Is it a functional interface? Let us ask the compiler for that. Indeed, it is a functional interface, so I can implement this functional interface using a lambda. I can get rid of this abstract stuff here. All right, so now I need to provide the lambda that creates that implements supplier. That returns a supplier of array. An array of supplier of E. I would like to write this lambda, this like that. All right. And this is my supplier. But for some reason, the compiler won't let me. Okay, I need to. Okay, the compiler doesn't work with this one. So I need to add this new supplier of E and tell it, hey, this is an array. But the compiler is still not happy. Welcome to the wonderful world of generics. Why? Because I cannot. Oh, sorry. Yes. Okay. It is still not happy because I cannot create a generic array of supplier of E here. The problem comes from the E here. So, okay, let us replace this with a wildcard. And now, of course, it tells me that it cannot convert this to an array of supplier of E, so I need to cast it like that. All right, and now I have only a warning, and of course, when I have a warning in this case, what do? I suppress it. Yeah! Wow! Victory. All right, and have a look at this. This is really beautiful. I can write it like that. See, Java has become nearly as unreadable as JavaScript. Hey, this really could be JavaScript, right? No, you don't think so? I'm not sure it's a progress, in fact. All right, okay, it's like that. Okay, great. So I have this off-static method, which is a factory method, to create my iterator. I'm very happy because I could implement an iterator using a lambda, which was not that obvious in the first place. I used this particular pattern that is, if I want sometime to return objects, sometime to throw an exception, I can do that with a supplier and call the get method, which is a nice trick, I think, that I can use in many places. And by the way, this functional interface is itself also a supplier, since it has only a get method. So I could here add supplier. Supplier of what? Supplier of that. Okay, so it makes really things particularly ugly, but it still works. All right. Oh, I still have the as next method to return, but this is really easy because I have only two suppliers to check. If the get method, if the get here is equal to this supplier, then it means that I don't have any more elements to consume in my iterator. So I think I can do something like that. Why isn't it? Yes, sorry. Get 0. Okay. If I just check what I have in my array, I can know if I still have elements to consume in this iterator. This is an iterator that works only for one object, right? It's a special kind of iterator. Well, this is not bad because now I have a lambda to implement a set, and that also returns a lambda as an iterator. Well, I like it. Great. Could I do the same for singleton list? Singleton list is the same kind of pattern. The difference being I have an indexed an indexed success to do it. So what did I do? I did, in fact, the same kind of thing. Oh, I've got plenty of stuff to implement. This size will return 1. Okay. the iterator, I probably can return the same object as the previous one, because the iterator doesn't take into account that this is a set or this is a list. So if I just singleton iterator, oops, dot of get, it will do the same. Empty returns false, of course. Contains O. I'm pretty sure that is the same as the singleton set. Where was it? I'm just going to copy paste this to get rid of all this. Oh, why doesn't seem to be happy? Oh yes, because that's a default method. I should make it public. No, I'm sorry, it's not abstract, it's public. Okay. Is empty, iterator, index of get index. This is in fact the same kind of trick as the iterator. If index is equal to 0, then I should return get. If it's not the case, then I should throw the new no such element exception. Such element exception. The problem is that I cannot throw an exception inside this operator. So what I can do, if I want to use it, to still use it, I can write things like that. Sub1 equal get. And the second one being this one here. Let's get rid of that. All right. This is sub2. As a matter of fact, I just need this sub2.get and get rid of this one. All right. So yes. So this, I'm still using this this supplier here and call the get method to throw the exception if I still want to use the ternary operator. And I could put this also in a static method to factor this code. Index of O, well, okay, so I should return either -1 if the object is not in the list, and 0 if the object is in the list. So do something like that. Get equals 0, and if not, -1. Last index, well, I guess I could do the same. Return index of O. Okay, I will let the list iterator on those three for the moment. Sorry, index of here. So you see that for the list. Okay, so now what I need to do is to make it an interface. Public. Replace them by default. Replace all. This is a public interface. It does not implements, but extends. This is not, well, I can also get rid of stack and say that also it extends supplier of E, and get rid of this method here. Now I can just copy paste the off method, off factory method of list here with the singleton list, and reach the same kind of pattern as the previous one, the iterator being the same. So with the same kind of idea, which is basically the application of the template method pattern from the Goph, I can use lambdas to create a list of and collections. Those were for the singleton. We could do the same for the 2 elements. Now for the 2 elements, the pattern is a little different. I'm going to go back to this class. I want a set of string, set 2. It's a 2-element set of 1, 2. All right. Let us create this method. There is one main difference with the pattern, which is generally speaking the same. Okay. Let us make this generic. This is a E. This is E1 and this is E2, right? And what I want to implement, in fact, is not a get method, but a get int method. And this int here is the index of the element, because I have 2 elements, so I need to tell which one is which one. Okay. The 2Array and the 2Array type method are almost the same. Instead of calling get, I have to call get0 and get1 to have the 2 elements. And all the mutation method are, of course, not supported. So this time, it is not a supplier that I'm implementing. It is a method that takes an int and returns an object. So it can be seen as a function that would take an integer and returns E. But in fact, in the Java util function package, I have an optimization for this kind of function, which takes I as a primitive type instead of an integer as an object. And this, yes, this is the int function of E. See, the int function, the abstract method takes an int, an index, and returns a value, an object. So this is exactly what I want. So of course I will make this an interface that extends sets an int function. Now I have to change, in fact, the name of this method, because the int function doesn't have a get method but an apply method. All right, not a big deal. So let us change this to the apply method. Hopefully it will also change. Oops. I think I asked too much to my Eclipse. I prefer to cancel this one. Okay, so first we are going to make this all the method default method, replace all, close. Okay, put back public here. So this is an abstract method. This is not a default method. Okay, this fixes all the compilation problem. Now, if I want to make this a functional interface, it is not a functional interface because I have a get method abstract here and a different method called apply in the int function there. So what I want to do is just, well, I'm going to get rid of this method because I don't need it anymore. And instead of calling get here, I just want to call the apply method in those two. Okay. So now I've got a functional interface, and I can implement this functional interface using a lambda, which is great. Let us do that. What is this lambda? This lambda takes an index as a parameter. It's an implementation of the int function there. If the index is equal to 0, I should return E1. And if it's 1, I should return E2. So it's fairly easy. I can just write it like that. Okay, and this is a 2-element set. It is not a regular set. right? So I can also, using the same kind of trick, implement two elements collections, here a set, using also lambda expression. Now, I could go further with 3 elements, 4 elements, and so forth. It would be just a little more complicated, but still doable. Would it be interesting from the point of view of performances? Probably not, because I will pay the price of dealing with this ternary operator, big if-then-else stuff, which would be probably costly. The contains object is going to return apply 0, which is the first element, equals O, or apply 1 equals O. This is nice because it will be lazily evaluated. I like that. And the contains all will be the same kind of implementation as the previous one. Let us make a nice little present to people who are going to call us with a null object. Hey, hey, exception. And c.stream the all match, and the all match this time will be e apply 0 equals e, or apply 1 equals e. And this time I don't have any method reference to for this one. These empty is of course false. The size is 2. And once again, I'm left with the implementation of the iterator. How can I transform this singleton iterator in a 2 elements iterator? Well, I guess I can do the same as this one. So I'm just going to call, I prepared another class called 2 elements iterator. So I'm going to create a factory method on it, 2 elements iterator dot off apply 0 apply 1, create this static method. Okay, I'm going to make an interface directly. I think you get the idea. Great. This is E1 and this is E2. And I want to extend iterator of E. Great. Hey, Mr. Eclipse, can you provide me the stubs for the methods directly? Yes, it's an interface. So it's not happy with it. So I need to implement just for Eclipse to give me the raw implementation, and now I'll make it an interface once again. Extend iterator, and it is an interface. Now I need to make this default instead of public. Okay, great. Let us do some cleanup. Great. So, in fact, what I can do is just take the code here. I'll probably, maybe I can just copy paste this and go from there and see what I can do from here. The code won't be very different. So yes, I've got a get method that if it's equal to no such element exception, it means that I have consumed all the 2 elements of my iterator. Now, the get 0, okay, it's a supplier and I want to return that. But I want in the get 0 to put the get 1 value. Okay. Let's just shift stuff. And in the get 1 value, in the get 1 in the get one, I want to have the no such elements exception. So when I first call this code, the get one will take the no such element exception. The one will go to the 0, and the second call, the one will go to the 0, meaning that the no such element exception will go to the 0, and the 0 will be thrown away. Great. So so I need a get method, which is my abstract method, which is going to return a supplier of array of supplier of E. Right? You should be happy. No, this should be written down. This. All right. Let us take back. Where is my singleton iterator? Okay, it's here. Let us take this factory method. Now I've got one supplier here and a second one here, but it's basically the same kind of stuff here. And I should be extending supplier of E array. Seems I have a problem here. Ah, is it this? Is it just the suppress warning? Excuse me, I've got a problem here I need to fix. Sorry? Oh, yes, excuse me. Okay, thank you. All right, so you see that the idea is exactly the same, in fact, and the type of this two-element iterator is the same as the previous one. Basically, I am using an array that is passed, that is created in the static method, but in fact that is passed as a parameter at the creation of the lambda. And I'm using the fact that I can mutate the content of this array here to have a next method that can return the elements of this array one by one. All right. And this will also work. So now, in my two-element set, oh yes, it's already done. I already wrote the implementation, right? Yeah, okay. So it's here. So I can just keep this here, and it will do the trick. So I can do it for singleton set, for two-element set. Same for the list. I'm not going to go through the two-element list because it's basically the same. We can also do the same for the maps. Where is it? I didn't create this. Yes, the map is here. For the singleton map, yes, I already created that. Singleton map can be seen as a two-element list. I do not necessarily need to create something with an integer as a parameter. I can do it with a Boolean, but basically it's the same kind of thing. So here I'll have one. Here, there. I am going to create an abstract method that returns an object, because the problem is that the type of the key and the type of the value is not the same. It's the difference with the list, and get something, and it could be a Boolean, for instance. Okay, and in the off method that takes a key and a value, I can just return an implementation of this boolean. I'm making a terrible mess here. If B is true, return the key. And if it's false, return the value. So it's a K and V. And it returns a singleton map of this. All right, this is an interface. It extends map of K and V. And I need to make all those defaults. Remove this one, remove this one, remove this one, and it should work. Okay, great. So this takes a boolean as a parameter, so I can also see that as a function of boolean and object. The problem being, since this get method has to return, excuse me, what I'm doing here. Doing a terrible mess here. Okay, this is the key. And this is the value. Thank you. Okay. I do not need this one anymore. Why isn't it happy? Okay, so if K is the key, I should return the value. If K is not the key, the deal is to return null. This is the contract of the map. Okay, sorry. This is the right way of doing that. Now, if I excuse me. No, this was the right way. This is not the right way of implementing the map. Let us get rid of that. Okay, I need to have the key and the value. Okay, so I need to have a method that takes a boolean and returns an object. This is what I need to have. Sorry, I need to because I'm not implementing a map. I'm implementing a singleton map. And if B is right, if B is true, then I return the key. Otherwise, I return the value. Okay? Right. Now, if I want a key set, the key set is, since I have a singleton set, I can leverage that. So singleton set of, and then I should return the key I am giving, so get true, and this returns the key, and this is the key. Okay, and suppress the warning, of course. Get rid of the override. And if I want a collection of values, I can do the same with the singleton set, for instance. Singleton set of, and the value is given by the get false. Okay, the false here will return the value. So, excuse me. Ah, c'est pas possible. Okay, and get rid of the warning once again. All right. I think I can import this. The entry set is a little more tricky because I need to check to create an entry here. So let us create this entry also with an interface that extends map entry. And in fact, this interface is roughly the same as the singleton map itself, because I need also a lambda that will store both the key and the value. So I can just take this in the entry and have an off method that will roughly do the same. This is the entry. Okay. And why doesn't it work? Ah, yes. I need to put default here. All right, so this is a functional interface now. The get key is just a return get true. And the get value cast to OK. And the get value is just a get false, like that, with a V. I can suppress the warning once again to have the same kind of thing. All right. So this is also an implementation of the entry using a functional interface and a lambda. So in my singleton map, I can just return a singleton set of my entry of get true, get false, which is doesn't work. Entry. Ah, yes. Okay. And V. Is that it? Maybe this guy needs a little help. I still have a compile problem. Oh, yes, because it's not the right entry. Let us put the full type of it here. And it should work. Right. I just need a suppress warning. And that will do the trick. Okay, so this is also my entry set. All those structures are immutable, so they will throw unsupported operation exception if I want to modify them. Remember that when I modify a key set, I cannot modify the value of the key, of course, but I can remove a key from a key set. I can remove an entry from an entry set, and since a key set and an entry set are views on the underlying map, I can it will mutate the map. But since the map is immutable itself, I'm not going to. It will just throw unsupported operation exception. Great. I could do the same for contains key. Want me to do it? Yeah, can do it. Let's quickly do it. So the contains key is just checking that get true, which is the key, should be equals to the key passed as a parameter. And the same goes for the value here. This time the get false, which will return the value. And of course the get method, a map should be able to return the get method. So if the key passed as a parameter is the same as the key equals key, then I should return the value, which is get false. Either I should return null because it is the contract of the map. Why is this guy not compiling? Just because I've got this one. Okay, and get false, of course, is a V. I'm pretty sure of that, so I can suppress the warning. Okay. So you see that we can also create an implementation of a map using a lambda. This time the abstract method we have implemented is just a Boolean here. We could have done it also with an index, just considering the 0 and 1 value. It would have been an int function. Here I did it with a Boolean, so in fact it becomes a function of Boolean on object with an apply method. I'm not going to do it because I would need to change all the get call to apply call to have the right stuff. And once again, it is a matter of identifying which abstract method I should be implementing. And once I have identified that, make the link with the right functional interface from the Java util function package and apply just the template method, which is basically a lambda with a default method in it. Right. Let's go back to the slides and some more bullet points. The fact is, if we bench stuff, we'll see that the singleton list, two-element lists are still faster than the ArayList. The ArayList itself is already quite fast, but I can go even faster if I use this kind of stuff. Why? Because I don't have any objects, no pointer chasing. It's only a lambda expression. This is the indexed read, so just the get 0. And the same goes for the iteration. Iterating of a set of just one object might seem a little weird, but I can end up doing that in my application. This is the iteration for the list, and the same goes for the with the iteration of the set. Now, you shouldn't be using that without a big warning. Is that there is a special contract in the collection interface considering the equals method and the hashcode method. And of course, since we are implementing collections, for those collections and maps with lambdas, we cannot override the equals and the hashcode method. Remember that we are not allowed to put implementations of the object class as default methods in a functional interface. This will not compile. So we still rely on the equals and hashcode method of the object class, and this contract will not be fulfilled. So if you want to use this kind of implementation, you just have to keep in mind that those are not real collections that should not be used in general applications as real collections. And it is time, I think, to conclude this talk. And I would like to cite Dr. Deprecated one last time. I love this kind of slide because it's just a copy-paste of something that is in the internet. So easy to do. Okay, so this is basically what Stuart just told you about when you should be using LinkedList versus ArayList. What we need to mention is that LinkedList and ArayList have been written 16 or 17 years ago. Java 2 has been released in 1998, so it has been written just before that. And at that time, the processors were not organized with these stacks of caches and pointer chasing problem that we have now and such. So LinkedList and ArayList have been are really objects from the past mostly that we are still using today because hey, it's like that. But the context has changed so much that well, there are things that were true 16 years ago that are not true anymore nowadays, and most probably in 15 years from now, it won't be true anymore once again. So we'll need to change everything from that. The second conclusion I would like to draw, especially from the second part of this talk, is that there are many patterns from the Gang of 4 that can be implemented using lambda expression. Here I applied mostly one pattern, which is the template method. Template method is just a lambda, and if you want to add method, all the concrete method, most of the time, can be implemented using default method, which is in fact very easy to do. There are other talks that have been made around here last year and in different places showing you how to implement builders, how to implement visitors, validators, strategies, etc., using lambdas that are very efficient, not necessarily very easy to understand, but these are really very good ways of implementing stuff from the Gulf. Avoiding pointer chasing is about reaching better performances. This is true for the moment. Maybe in the next years to come, in the 10 years to come, it won't be true anymore. But right now, really the most performance structures you can use are are structures without pointers. That really is not such a good news, as you said, Stuart, for immutable structures, because basically we have two immutable structures in our toolbox: the linked list for the immutable list, and the trie tree for the map. And the trie tree is a structure based on pointers once again. And with that, I think I'm done with this talk. Thank you very much for your attention. Do we have still time for questions? Indeed, we have. Did you notice any questions, Stuart, on Twitter?
Well, I contributed some comments.
You need the mic. Sorry.
No,
Yeah, please.
Okay, well, thanks for bringing me up again. So I contributed some comments about this, which there was some back and forth on. So sorry you're reading it for the first time here. Of course, I had to quote your Java has become nearly as unreadable as JavaScript. That had to go on Twitter right away. So it's interesting, at the end you said this technique should be avoided. And one thing I picked up in the middle of this is when people write lambda expressions, they want to capture and mutate local variables. And so that doesn't work. And so you have to use the single element array trick. And so we at Oracle are pretty allergic to that. So I do not recommend using it. And in the same example, actually, this is actually, I mean, the single element array trick is dangerous, but if you contain it properly, it can be correct. I think that one of the examples you used, identity comparison on a lambda, and and so there the problem is that the identity semantics of lambdas are not defined.
Yeah.
And so in an update release, we might say, oh, here's a different way to use invoke dynamic, and you might actually end up getting a different lambda instance if you do that, which will break that code. So that I think is pretty dangerous.
I think it can be, we can overcome this problem in this particular implementation.
Sorry, what's that?
Yes, well, I mean, instead of using the lambda itself, we could use some kind of constant inside the interface, because we can have
I think so.
public static final in interfaces still.
I have to scroll past all the retweets of Devox Trump here.
Oh, come on, guys. Hey, this is supposed to be a serious conference.
Oh, did you want to talk about JMH and Java 9?
Oh, yes. What you mentioned is that you were not sure that JMH was a part of the Java 9 distribution, as I said. All right. So maybe it's not, in fact.
Yeah, I don't think so. It's not part of the JDK. So JMH is out there. It's on OpenJDK. It's in a different repository. Yeah. I think it's under the Code Tools repository. And it gets released every so often. It is available on Maven, and so it's available independently of the JDK. So I'm not sure where the Java 9 linkage came from, but yeah, you should definitely. I mean, it's I think it's reached 1.0. It's pretty stable, very useful.
Yeah.
Excellent benchmarking framework from Alexei Shiplov.
Yeah. Okay. Well, if we're done. Okay. Thank you very much. The slides will be on SlideShare.
I'm saying, hey,
please. The slide will be available on SlideShare soon. I will tweet that using the hashtag you saw. And most of the code of the benchmark are on my GitHub account, so you can check also. And I put the updated version of the benchmark on my Twitter account also very soon. So thank you for your attention, and have a good DevOps. Thank you.